Good morning, everyone, and welcome to this lecture. And in this lecture, we are going to deal with X-rays. What do you mean by X-rays? Any ideas? What do you mean by X-rays? Any idea what is X-rays? No one? Have you heard the term X-rays anywhere?
Yes, sir.
What do you know about them? Hmm? No one? I think I had shown you something known as the electromagnetic spectrum. Did I show you that?
Yes, sir.
What was electromagnetic spectrum? Do you remember that electromagnetic spectrum that I showed you?
Yes, a different kind of race.
Different kind of rays. Okay. Different kind of rays. Let me again try to show you. Different types of rays. Electromagnetic spectrum
With the different wavelengths, sir.
with different wavelength. Anything else? Okay. Since you don't recollect anything, we have this something known as the electromagnetic spectrum. Now, what is this electromagnetic spectrum? It gives us whatever rays or whatever type of radiations we have. As you can see over here, this is written in increasing order of frequency. Frequency is increasing, and wavelength, if you talk about wavelength, wavelength is decreasing. Frequency is increasing and wavelength is decreasing. Do you understand this?
Yes, sir.
So, what do you understand by X-rays then? Frequency is increasing. What are X-rays? Hmm. Hmm. Yes. No one has any idea. As you saw on that electromagnetic spectrum, looking at the electromagnetic spectrum, what do you understand by X-rays? Where does X-ray lie? Do we understand anything? Looking at that diagram that I showed you, did you understand anything? Looking at the diagram,
Yes, sir.
what did you understand?
It lies between gamma rays and ultraviolet.
It lies between.
Gamma rays and UV rays.
What do you mean by gamma rays? What do you mean by UV rays? If you understand X-rays in terms of gamma rays and UV rays, you must understand what is gamma ray and what is UV ray. What is gamma ray? What is UV ray? What is gamma ray? What is UV ray? So X-rays are electromagnetic radiations. X-rays are electromagnetic radiations of very short, very short what? Very short what?
Wavelength.
Very short wavelength and high, high what?
Frequency.
When the frequency is high, what about the energy?
It is high, sir.
High frequency and high energy. X-rays are electromagnetic radiations. They come in the electromagnetic spectrum and they come only next to the gamma rays. Gamma rays are the rays which have the maximum energy. Gamma rays have the maximum energy and they are the most dangerous radiations in this universe. Sometimes you see these gamma rays being emitted when universes collide and when a star dies. We have this gamma ray burst that you see. Obviously, you don't see with your naked eyes. You see it with high range telescopes and the Hubble telescope and all those gamma ray bursts. Gamma rays are the most dangerous rays, and that is why this danger sign, because they are radioactive, very high energy. As you go down, then you have visible and ultraviolet light. Visible light is not so dangerous for us. We are everyday. subjected to radiation in the visible range. Now, when we talk about this gamma, when we talk about this X-rays, gamma rays or gamma radiations will also come in the next class, maybe tomorrow. Right now, we are concentrating on the higher end of the spectrum. The higher end of the spectrum. If you look at the hydrogen spectrum, we had seen where all the different lines of hydrogen spectrum lie. Do you remember? Where does the line of Lyman series, Balmer series, Passion,
Yes, sir.
Bracket, and Profound series lie? Do you remember that?
Yes, sir.
Where? Anyways,
UV, Lyman UV,
Lyman UV
Palmer visible, and
and the rest are infrared, so they are not so harmful because the wavelength is less. They are not radioactive also. X-rays are radioactive, and these are electromagnetic radiation, so very short wavelength but very high energy. The wavelength of X-rays is very short in compared to the wavelength of light, hence they carry much more energy. They are invisible, we cannot see this. Above red, you cannot see anything. They travel in a straight line with the speed of light. They are electromagnetic radiation. Their X-rays are measured in Roentgen, and this Roentgen was a gentleman who actually discovered it. We'll see that. X-ray carry no charge, so they cannot be deflected by electric and magnetic field. Lambda of gamma rays, which are more stronger, questions are coming on this, is less than gamma of X-rays, is less than the gamma of UV rays. Lambda of UV rays. We understand this. Where are X-rays used? Crystals. They ionize the gases through which they pass. I'll give you 2 minutes to note this down. Questions are coming based on these properties. Then we keep on and writing the important points. X-rays have high energy. They have high energy. They can pass through the bones of human beings, but they don't have that much energy that they can pass through heavy metals and heavy bones. They cannot pass through heavy metals and heavy bones. They can pass through your skin. They cannot pass through your bones, and that is why you have all those X-rays coming up. The effect photography plate, that is for use in medical purposes. Long exposures over X-rays is injurious. They are radioactive, as you can see, and people who have X-ray lab, they suffer cancer very often. Lead is the best absorber of X-rays, so all these labs they have coating of lead which can absorb these X-rays. They produce photoelectric effect and Compton effect. We will see what is this Compton effect. X-rays are not emitted by hydrogen atom. We have seen that. These rays cannot be used in radar because they are not reflected by a target. They are absorbed. They are not reflected. You only use X-rays for taking that inside your body stuff. That is where it is used. Since they are electromagnetic radiation, they will show all the properties, reflection, refraction, and all those things. When X-rays are incident on a surface, they will exert pressure on the surface. In the last to last class, we had seen the pressure exerted by radiation on the surface. So whatever we have studied there, it is also applicable for X-rays. We understand this?
yes, sir.
Note them down first. And as you can see, when X-ray pass through a body, they have got high energy. They can go through this body. If I naught is the intensity of the incident X-rays, the X-rays which emerge out, I, the value is given by I naught e to the power of minus mu x, where mu is known as the absorption coefficient and x is the thickness of the material that is used. Do we understand this?
Yes, sir.
I dash is the intensity of the absorbed radiation. Do we understand this?
Yes,
I dash is the intensity of the absorbed radiation. Now, sometimes they ask you this question: after how much x Will the intensity becomes half? That is known as the half value thickness. Do you understand? Half value thickness. It is the thickness of the material where the intensity becomes half, and that half is 0.693, and this 0.693 is going to come many times from now on. 0.693 by mu. I've done nothing. I've just put I dash as I naught by 2 and calculated it. Do you understand this?
Yes.
I'll give you 2 minutes to note this down. Now, we have seen what are X-rays. We have seen the properties of X-rays. Let us move ahead and try to understand them in a more systematic way. Now, to understand X-rays, we have to understand how these X-rays are produced. How these X-rays are produced? Any idea? How these X-rays are produced? Who discovered these X-rays? Let me put the question in this way. Who discovered these X-rays? Yes. Who discovered these X-rays?
No idea, sir.
You have no idea who discovered these X-rays? Okay. These X-rays were discovered by a scientist, obviously. Accidentally, probably. He had no idea what these rays are, and hence he gave it the name. What name? X-rays. They were discovered by a scientist by the name of Roentgen, and therefore they are also sometimes known as Roentgen rays. He did not know what to name them. He just discovered them. He did not know what to name them. In maths, if it is an unknown quantity, he used to name them X, and therefore he named them X-rays. Now, how did he produce X-rays? To produce X-rays, we need three important things. What are these three important things that are needed to produce X-rays? Obviously, you have no idea. Since you have no idea who discovered X-rays, you might not have any idea of what are required to produce X-rays. What is required to produce X-rays is, let me put it in a different way. We see what Roentgen discovered. Let me try to make you understand. What did Roentgen discover? So he had something known as a discharge tube. I'll show you that discharge tube. He had a discharge tube, and he kept the discharge tube almost evacuated. So the discharge tube was evacuated. It was having vacuum, and he applied a very high potential difference on that discharge tube, Coolidge tube we call it, and he saw some unknown radiation coming. And those radiations, since he did not know what those radiations are, he started to call them X-rays. Now we know how X-rays are produced. The basic premise is like this: fast moving electrons when fast moving electrons strike a metal plate, of high atomic weight. When fast moving electrons strike a target material whose atomic weight is high, X-rays are emitted. So, in order to produce X-rays, what are the essential things that we'll require? Yes, now I want to produce X-rays. I have told you to produce an X-ray. How, when are X-rays produced? X-rays are produced. I've told you how, what is required to produce X-rays. Now, can you tell me what will be required? If I want to produce X-rays, what do I need?
Evacuated discharge tube.
I will need, okay, an evacuated discharge tube. What else?
Fast moving electrons in it with the high potential difference.
Why high potential difference?
Because frequency is high.
So to produce X-rays, I need high speed electrons. So first of all, I need electrons. So I need a source of electron. Then I want them to be of high speed. Therefore, I need an arrangement to accelerate the electrons. And how am I accelerating these electrons? I'm accelerating these electrons with a high potential difference. So I need something to give me electrons. I need something to accelerate it. And then I need the third thing. What is the third thing? I need a target, a heavy metal, a heavy substance, high atomic weight when I say heavy, and also high melting point. Why high atomic weight and high atomic point, high melting point? We'll understand this. On which the electrons, the fast moving electrons will strike. So if I have these three conditions fulfilled, I should have X-rays being produced. X-rays are produced when fast moving electrons strike a target of high atomic weight and high melting point. If I can have these three conditions, if I can have fast moving electrons striking a high atomic weight target, I will have X-rays being produced. I'll give you 2 minutes to note this down. Now these X-rays are produced in what we call as the Coolidge tube. This is what a Coolidge tube looks like. I'll try to explain what is the Coolidge tube. You draw it patiently so that you understand. No one is going to ask you the diagram, but it's important to understand the diagram because 90% of the question on X-rays are based on this diagram. Now, looking at the diagram, do you understand anything? Looking at the diagram, how was X-rays produced? Do you understand this? Do you understand anything? I'll give you 5 minutes. Draw the diagram and also make me understand how X-rays are produced. Can you do that for me?
Yes, sir.
5 minutes. Draw the diagram calmly and then try to make me understand what is happening here. Can you explain what is happening here? If you can explain, that means you have understood this. The questions will come automatically. Yes, what is happening here?
Sir, basically electrons will travel from cathode to anode.
Where is the cathode?
Filament.
Filament. What is the function of this filament? This is the cathode. C, cathode. This is the filament. You see this pink thing? This is the filament. What is the function of this filament?
Uh, they emit electrons.
How does the filament emit electrons? This filament is going to emit electrons. By which process? What is the symbol of the filament that you see? How does it look like? How does the filament look like?
Inductor.
It looks like a heater. I again repeat my question. How does the filament produce electrons? How does the filament produce electron? It has a large number of electrons, it gives it for free. How does the filament produce electrons? Yes. How does the filament produce electron? The filament produce electrons by the process of thermionic emission. It consists of a heater. You heat up that heater. You heat up the filament. If the heat is enough, electrons would be emitted. That is your purpose of the filament. It produces electrons by the process of thermionic emission. Thermionic emission. So this filament has a current I which flows in this filament. Because of this current I in the filament produces electrons. Okay, so electrons are now produced. Then what happens?
They travel to cathode, anode, sir.
How do they travel to anode? Now comes the second element, and the second element is the potential difference V. This potential difference should be very high or should be very low?
High.
The potential difference should be very high. Why it should be very high? Why it should be very high?
To electrons to gain high energy.
The electron should gain a very large kinetic energy because we need very fast moving electrons. So this is the purpose of this battery. The filament is made cathode, and now we have come on the right hand side, and the right hand side we have the third element. The third element is anode, which basically consists of T. What is this T? What is this T?
Metals.
This is the target. This is the target metal or target material. What should be the property of this target material? It should be a
High,
material of,
high atomic weight and high melting point.
when this high fast moving electrons strike this target metal, we see jig 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 jig. Do you see the jig 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 jig?
Yes, sir.
The jig 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 are
X-rays.
In a way, if you look at this jig, 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 and you look at this entire arrangement, you may think it of as the reverse process of something. Which process this is the reverse of? Electrons falling, dhang, X-rays emitted, dhang.
Photoelectric effect.
It is sort of the reverse of photoelectric effect. How it is the reverse of photoelectric effect?
In case of X-rays, photons are striking the metal.
Not photons are not striking the metal. X-rays. Photons are not striking the metal. Try again. If you look at this Hertz experiment, rays were falling on a photosensitive surface and photoelectrons were emitted. Rays were falling, electrons were emitted. Rays were falling, electrons were emitted. If you now look, electrons are falling, X-rays are emitted. So in a way, it becomes the reverse of photoelectric effect. Do we understand this?
Yes, sir.
Everyone has drawn the diagram.
Yes, sir.
Then you can see the explanation of all these particles and you have to write them quickly, the important points. What does a Coolidge tube consist of? A Coolidge tube consists of evacuated glass tube. We need vacuum. Contains cathode and anode. Anode is the target. What is the cathode made up of? It is a tungsten filament. Tungsten. This filament is coated with oxides of barium or strontium to have emission of electrons even at low temperatures. If you coat them with barium and strontium, even at low temperatures, you will have electrons emitted. This filament is surrounded by a molybdenum cylinder, which is kept at a negative potential with respect to the target. The target, which is a metal of high atomic weight, high melting point, and high thermal conductivity, we will see why it is. It's again made of tungsten or molybdenum and is embedded in a copper block. It is embedded in a copper block. Why it is embedded in a copper block? Let's see. The filament is heated by passing current through it. So there is a current which is flowing in the filament. Do we understand this?
Yes.
Because of this current, the filament is heated. And because of this heating up, the filament emits electron by thermionic emission. And that is why I told you thermionic emission. A high potential difference is applied. This high potential difference which is applied accelerates the electron which are emitted by the filament. This stream are focused on the target. Remember, most of the energy is converted into heat, so the target metal gets heated up. Very high heat is produced in the target metal, and that is why it is surrounded by a copper anode, so that whatever heat is generated, it is transmitted, and therefore you have a water pipeline. Do you see this water in that thing?
Yes, sir.
You see this water? Jig, 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 this water is running. This water is running so that it can cool this target. Otherwise, the target will become very hot. And this anode is again made up of copper so that it conducts most of the heat out. So I hope you are able to relate this with the diagram. Now remember, most of the energy is converted into the form of heat. Only 1 or 2%, is converted into X-rays. Only 2%. During the operation of the tube, a high quantity of heat is produced. This heat is conducted through copper anode to the cooling fans from where it is dissipated. Do we understand this?
Yes, sir.
This is the entire process of production of X-rays. I'll give you 2 minutes, 3 minutes to note it down. Let me know once you are done. We can have a look at the characteristics of the target. The target metal must have high atomic number to produce X-rays which are hard. What do you mean by hard X-rays? I'll tell you, don't worry. It must have high melting point, and it is very evident. Why it should have high melting point?
Because heat is produced.
Large amount of heat is produced. If it does not have high melting point, it will melt and it will just become liquid and nothing will happen. It should have high thermal conductivity. Why it should have high thermal conductivity? So that it can conduct and remove the heat which is produced. Tantalum, platinum, molybdenum, and tungsten are ideal target metals. Now, whenever we talk about X-rays, there are two things that we talk about X-rays. The first thing is intensity of X-rays. Now, instead of calling it intensity, we can call it the quantity of X-rays, or you can talk about the number of X-rays. If you remember, in photoelectric effect, we also talked about intensity, and whenever I talked about intensity of radiation, I always talked about what? Whenever I refer to intensity of radiations, I told you whenever I talk about intensity of radiation, that means what? We are talking about what? We are talking about number of photons which were falling. Here, whenever we are talking about the intensity of X-rays, we are talking about the number of X-rays that are produced, the quantity of X-ray that is produced. Now, the quantity of X-rays or the number of X-rays depend on how many electrons are striking the target. Number of electron depends on the temperature of the filament, which is dependent on the filament current. Therefore, I can write, my dear friend, intensity or the number of X-rays is directly proportional to the temperature, which is directly proportional to the current of the filament, which is directly proportional to the voltage of the filament. I am writing it as Vf because there are two voltages here. There are two voltages here. As you can see, there are two voltages here. One is the potential difference between the cathode and the anode. Here, I can just apply a small battery and I will call it as Vf. So it depends on the voltage of the filament or the current flowing in the filament. More the current, more the temperature, more the number of, more the heat, more the temperature, more the number of electrons, more number of electrons striking the target, more number of X-rays are produced. That is known as the quantity or the number or the intensity of X-rays. The second thing that we are considered about is the penetrating power of the X-rays. Now, whenever we talk about this penetrating power, instead of calling it as the penetrating power, we can also refer as the quality of X-rays. What is the quality of X-rays? Or you can also refer to the energy of X-rays. Now, this energy of X-rays will depend on the frequency of X-rays. More the frequency, more will be the energy, more will be the penetrating power, more will be the quality of X-rays. It depends on the energy of the incident electron. More energetic electron will have more energy. It will impart more energy to the target metal. and hence we will have more penetrating power X-rays coming out. That means the penetrating power or the energy of X-rays is directly proportional to the applied voltage V between the cathode and the anode. Do we understand this?
Yes, sir.
Take a deep breath, close your eyes, open your eyes, read it 5 times, and then write it. There are two things that we have to consider here. One is the number of X-rays or the quantity of X-rays or the intensity of X-rays. That means we need more number of X-ray photons. 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 That depends on the filament current. For more energetic photon, we need more voltage. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. Now we come to this part where we understand how we can classify X-rays based on the penetration power. X-rays are of two types. It's very easy to understand why one is known as hard and the other one is known as soft. Soft will have less penetrating power, hard will have more penetrating power, soft will have less frequency, hard will have more frequency, soft will have more wavelength, hard will have less wavelength. How much is the wavelength? You don't need to know this, but hard has a wavelength. Oops, color has changed. Hard has the wavelength from 0.1 to 10, and soft has a wavelength from 10 to 1. How do you find the energy from the wavelength? Hc by lambda, remember that?
Yes, sir.
The important thing is the use. Hard X-rays are used in radiotherapy. You might have heard that when someone has a cancer, he has to undergo radiotherapy. Hard X-rays are used. For radio photography, soft X-rays are used. Do we understand this?
Yes, sir.
I will give you 2 minutes to note this down. Then we move on and see how are X-rays classified on the basis of by what process they are produced. And what do you mean by process they are produced? Now, we know how X-rays are produced. This is a target of high atomic weight and all those things. And these electrons are striking this target metal. Now, when these electrons, these high-speed electrons are going to strike this target metal, they are going to penetrate the target. Once they are getting inside this target, they are losing their kinetic energy, yes or no? And they might come to rest inside the metal. The electron, before being finally stopped, is going to collide with the atoms in the target. Yes or no?
Yes, sir.
Now, there are two types of things that can happen. The first thing that can happen is because of the positive nucleus of the atom, the electron is deflected from its path. Do you see this electron getting deflected from its path? Do you understand this?
Yes, sir.
Now, when it's getting deflected from its path, it is losing energy. The electron is deaccelerating. So the energy with which it enters, half mv1 square, and the energy with which it leaves, half mv2 square, is not the same. There is a decrease in energy. And if we assume that there is no heat loss, there would be some heat loss. So some energy will be lost in the form of heat. The rest of the energy will be coming out in the form of jig 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 jig. Do you see this jig 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 jig? This jig 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 is the X-ray which is emitted. This type of X-ray which is emitted is known as This green X-ray which is emitted is known as a continuous X-ray, and the spectrum formed is known as continuous X-ray spectrum. Do we understand this?
Yes.
Everyone understands this?
Yes.
So these continuous X-rays are obtained when the striking electron approaches the nucleus, and because of the electrostatic attraction, it is slowed down. This X-ray is known as continuous X-ray. I'll give you 2 minutes to note this down. Then we move on to the next important aspect. Remember, this continuous spelling is wrong. These continuous X-rays are produced by a phenomena. I think it's a German word, Bremsstrahlung. It means slowing down or breaking. You understand? Electron is slowing down, and the radiation which is produced because of this is continuous X-rays. Do we understand this?
Yes, sir.
Now, depending on the kinetic energy, if the electron loses its entire kinetic energy, in this way, the X-ray which will be produced will be having maximum energy. Do we understand this?
Yes, sir.
This maximum energy will have maximum frequency, and this maximum frequency X-ray will be having minimum wavelength. Yes or no?
Yes, sir.
This wavelength is known as lambda min. Do you understand the meaning of lambda min?
Yes, sir.
And the frequency is known as maximum frequency of X-ray which is produced. This frequency max is directly proportional to the applied voltage. Do we understand this applied voltage E? Because of this applied voltage, only the electron is getting accelerated. And if this accelerated electron loses the entire energy in the first collision, you will have the X-ray with maximum energy or maximum frequency or minimum wavelength. So this lambda min is inversely proportional to this applied voltage. Do we understand this?
Yes, sir.
Everyone understand this? Yes or no?
Yes, sir.
So it will be HC by EV, or HC can be done as 12,375. Remember that 12,375 and 12,400 is coming so much. Now, this wavelength is also known as the cutoff wavelength. This cutoff wavelength depends only on the accelerating voltage. Yes or no?
Yes, sir.
Very important point. It does not depend on the material of the target. That means if you have two targets of different materials with the accelerating voltage same, the minimum wavelength would be same. Do we understand this? This chapter, you may not get a numerical from this chapter. You will only get theoretical questions from this chapter. These all things you must remember, that this frequency maximum or this lambda minimum depends on voltage. Frequency is directly proportional to the voltage. Lambda is inversely proportional to the voltage. It does not depend on the type of the metal that is used or type of the target metal that is used. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. Then comes this graph. And as you can understand, when I say continuous X-rays, this continuous X-rays will have all wavelengths above a certain minimum wavelength. Do you see this? Above a certain minimum wavelength, you will have all the wavelengths of X-ray coming. This spectrum is known as the continuous X-ray spectrum. Do you see this?
Yes, sir.
And this minimum wavelength depends on what? This minimum wavelength is inversely proportional to V. Do we understand this?
Yes.
This spectrum is known as the continuous spectrum, and the minimum wavelength only depends on V. Do we understand this?
Yes, sir.
On the right hand side, we see two different metals, but with the same voltage, lambda min is same. Do we understand this?
Yes.
When the voltage is changed to V dash, lambda min become less. Do we understand this?
Yes, sir.
We just need to draw the graph. Do it fast so that we can move on to some questions. Let's move ahead with the question. And this is the first question that we are going to do. The minimum wavelength of X-ray produced in a Coolidge tube operated at a potential difference of 40 kilowatts. Not watts. 40 kilovolt is how much? I'll give you a minute to do it.
So it is 0.31
So,
amps.
what is the answer? Lambda min. You can write it as 12,400 divided by your voltage. Yes or no? Voltage is 40 kilovolts. So, 40 into 10 raised to the power 3. 40,000. The answer would be how much?
Yes.
The answer would be A.31 Armstrong unit. I hope you are able to understand this. Yes or no?
Yes.
This is the next question. The cutoff wavelength of continuous X-rays from two Coolidge tube operating at 30 kilovolt. One is having molybdenum and the other one is having tungsten is. And the answer is you don't even have to calculate. Yes or no?
Yes.
The only option which has both the options same are 0.414. It does not depend on the metal. It only depends on the accelerating voltage. Do we understand this?
Yes.
Next one. An X-ray tube operates at 20 kilovolt. A particle electron loses 5% of its kinetic energy to emit a X-ray photon at the first collision. Find the wavelength of this photon. I'll give you a minute to do this. A minute to win it. Minute to win it. So how are we supposed to solve this? We can write the kinetic energy of the electron will be equal to 20 into 10 raised to the power 3 electron volts. Yes or no?
Yes.
Now the energy which is converted into X-ray is 5%. So the energy of the photon of X-ray, the energy of the X-ray photon will be 5% of this. So that is equal to 5 by 100 into 20 into 10 raised to the power 3. Yes or no? Electron volt. Yes or no?
Yes.
So that becomes 1000 electron volts. Yes or no?
Yes, sir.
That should be equal to 12,400 divided by lambda, hc by lambda. I hope you understand this. Hc by lambda, 12,400 divided by lambda. So my lambda becomes 12,400 divided by 1,000. 12.4 Armstrong unit is the answer that I was looking at. I'll give you a minute to note this down. Everyone has understood this.
Yes, sir.
Then we have the next type of X-rays, my dear friend, which is known as characteristic X-rays. Now, this X-ray depends on the target metal. It depends on the target and it does not depend on the accelerating voltage V. Now what happens? You can see this electron going jig 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 jig. Do we see this electron going jig 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 jig? Now because of this getting deflected, the X-rays which are produced are known as continuous X-rays. Do we understand this?
Yes, sir.
That is a continuous spectrum and we have also seen its graph. But now what can happen is when it is going jig 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 jig, it can also do pick 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 pick. What pick 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 it can do? It can remove an electron from an inner shell. Do you see this electrons getting removed from the inner shell?
Yes, sir.
It can strike an electron which is moving in its orbit and it can strike it from its orbit, from inner shell. Yes or no?
Yes, sir.
But electron in an inner shell, vacancy in an inner shell cannot remain vacant. Yes or no?
Yes, sir.
So then what will happen? Electrons from the outer shell will jump from outer shell to inner shell. Yes or no?
Yes, sir.
And we know that when electrons jump from higher orbit to lower orbit, what happens? What happens? They emit jig 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 jig, and this jig 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 is known as
energy
the
limit.
characteristic X-rays. Do we understand this?
Yes.
So characteristic X-rays are emitted. These characteristic X-rays are emitted. These characteristic X-rays are emitted. When they are emitted?
Ooh.
When the fast moving electrons do what? When these fast moving electrons dislodge a inner shell electron and electrons from higher shell, they move towards inner shell. Do we understand this?
Yes.
This is all that you need to understand. Draw the diagram. You don't have to write the entire Ramayana. No one is going to ask you the entire Ramayana. Just write it in your own language: Hindi, English, Tamil, Telugu, Malayalam, Urdu, Farsi. I don't understand. I don't know. Just have to remember these 3 points, nothing else. I'll give you 2 minutes to note this down. Now, depending on from which shell the electron has been removed, there are a number of series. K series, L series, M series, oops, and so on. Do we understand this?
Yes.
Now, in K series, what will happen is electron will be removed from the K shell, and from higher shell, electrons would be coming. The first is transition is from L to K. That is known as K alpha. Do we understand K alpha?
Yes.
Alpha means the first line. Then electron can jump from M shell to K shell. That series is known as beta. Do we understand K beta?
Yes.
It can jump from N shell. It will be known as K gamma and so on. K alpha, K beta, K gamma, L alpha, L beta, L gamma, M alpha, M beta, M gamma, and so on. Do we understand this?
Yes.
I'll give you 2 minutes to note it down fast. Then we can move ahead and see the various series. Just for example, K alpha, the transition will be from L to K. Do we understand this?
Yes.
So the difference in energy between the two levels, my dear friends, will be equal to frequency into h of K alpha. Do we understand this?
Yes.
So from there you can find out the lambda of K alpha series. It will be 12,400 divided by EL minus EK. Do you understand?
Yes.
Similarly, you can find out the gamma, the alpha for K beta series. It will be like this, yes or no?
Yes.
You can also find out the wavelength for any of the series. The wavelength does not depend on accelerating voltage. It depends on the atomic number, and therefore it depends on the material. Lambda of K alpha is less than lambda of L alpha is less than the lambda of M alpha. Similarly, frequency of K alpha, you can see it from the calculations that are there. Yes or no?
Yes.
I'll give you 2 minutes to note it down. Note it down fast. Let's move ahead then and then see the intensity versus wavelength graph. The complete intensity versus wavelength graph will look like this. This pink line that you see is continuous X-ray. Do we understand this?
Yes.
This pink line will be continuous X-rays, and they will be continuous always. They will extend till infinity. Do we understand this?
Yes.
And in between you will have these spikes, and these spikes will represent the characteristic X-rays, and you can see K alpha wavelength is more than K beta. Do we see this?
Yes.
L alpha wavelength is more than L beta, L gamma. Remember this, keep this in your head. Questions based on this will be based on this. Do we understand this?
Yes.
I'll give you 2 minutes to note this down. Then this is a very simple question. Which line is K alpha? Which line is K beta? Give me the answer first.
2 is K alpha and 1 is K beta.
2 is K alpha and 1 is K beta. Do we understand this, everyone?
Yes.
Everyone understand this?
Yes.
Then the next one. Which one is K alpha and which one is L alpha? Which one is K alpha and which one is L alpha? Which one is K alpha? Which one is L alpha?
1 is K alpha and 2 is L alpha.
Anyone understands this? Yes or no?
Yes.
Shall I move ahead? Shall I move ahead?
Yes.
Then you must note down these points as well. If we miss this graph, the wavelength of continuous X-rays they will range from some minimum free wavelength to maximum. Here are the graphs. The graphs are important. This is a graph between F max and V. It is directly proportional. Do we understand this?
Yes.
If you draw the graph between log of F max and log of V, the graph will be same, but it will not start from 0 because nothing can be log of 0 is not defined. Do we understand this? So it will start from somewhere else. Lambda min and V, the graph will be like this. Log of lambda min and V, the graph will be like this. Everyone understands this?
Yes.
I'll give you 2 minutes to note this down. Then we come to the last topic of this is known as the Moseley's law. Have you heard this name Moseley?
Yes. Sir.
Who was Moseley? Who was Moseley? Who was Moseley?
Mm. Discovered modern periodic table.
He discovered modern periodic table, and now we are going to see how he discovered this modern periodic table. He studied the characteristic X-rays of many elements and observed that the square root of the frequency of the K alpha line, square root of the frequency of the K alpha line, or square root of frequency is directly proportional to the atomic number, or frequency is proportional to z minus b the whole square, or frequency is equal to a times z minus b square, where z is the atomic number, f is the frequency, b is a constant which is known as screening constant. For alpha series it is 1, for K series it is 1, for B series it is, for L series it is 7.4, for M series it is 9.2. A is a proportionality constant, and you can compare it with the Bohr model. You can find out that this A will be equal to RC into 1 by N1 square minus 1 by N2 square. Do we understand this?
Yes.
If you plot a graph between root over frequency and Z, the graph would be a straight line. Do we understand this? Yes or no? No, yes.
Yes. Sir.
Everyone understand this? Yes or no?
Yes. Sir.
This screening constant, this constant A, it does not depend on the nature of the target, but it depends on the transition. Do we understand this? Will you be able to remember this? We have just now seen Bohr's atomic model. Yes or no?
Yes. Sir.
Everyone can understand this?
Yes. Sir.
I'll give you 2 minutes to note this down. Anyone having any doubt on this?
No.
Now, these are some important points about Moseley's law. This Z minus B sometimes is known as the effective atomic number. In this way, Moseley actually corrected Bohr's model and made it better. It supported Bohr's theory. It experimentally determined the atomic number of elements. You just need to remember them. It tells us that the periodic table must be in the form of atomic number. The gaps were, if left some gap in the atomic table, they were later found out to be metals. The atomic numbers of some elements were established. Then you have this formula. We have already written this formula. Yes or no?
Yes.
Remember this formula, and the energy of the characteristic X, the energy of the photon emitted by the characteristic spectrum will be given by this formula. Do we understand this? Depending on from where to where the jump has been made. We understand this.
Yes.
Continuous X-ray, all wavelengths are possible. For characteristic X-rays, we have to use this formula after Moseley's collection. Do we understand this?
Yes.
I'll give you 2 minutes to give me the answer, to note this. Then you can find out the value of A. Remember that A? You can find out the value of A if the transition is from n is equal to 2 to n is equal to 1, the value of A will be root over 3c by 4. Do we understand this?
Yes.
Everyone understands this?
Yes.
You can also find out the frequency for K alpha series. For K alpha, the first orbit is n1 and n2. We know from second to first it is shifting. Yes or no?
Yes.
Everyone understands? Lambda, for general formula for lambda, for alpha, for K series will be 1 minus 1 by n square. Do we understand this?
Yes.
Everybody understand what is written here? It's just the Bohr's formula. The only difference is instead of Z, it is written as Z minus B. Do we understand this?
Yes, sir.
I'll give you a minute to note this down. Again here, left hand side Bohr's model, right hand side Moseley's correction. Do we understand this? This is for K alpha series because B is taken as 1. Do we understand this?
Yes.
Side by side?
Yes, sir.
1 minute I'll give you. Then, as you can see, you can find out the characteristic X-rays for, you can find out the wavelength of characteristic X-rays using Moseley's formula. If the target is same, that is Z is same, lambda will be proportional to 1 by n1 square minus 1 by n2 square. Do we understand this?
Yes, sir.
Question is same. If a question comes of characteristic X-rays, it is same as the question that we had done in Bohr's model. What is the wavelength from 3 to 1? What is the ratio 3 to 1 to 2 is to 3? We can find it out from here, yes or no?
Yes.
If the transition is same, then lambda will be inversely proportional to 1 by z minus b square. Do we remember this? Do we understand this? Same question of Bohr's. When a transition is made from third to 2 or 1 or 2 to 1 or 4 to 2, same question can be made for characteristic X-rays. Do we understand this?
Yes, sir.
I'll give you a minute to note this down. In this graph, you see at the same cutoff voltage, V is same. So both the X-rays are starting from the same point, from the same wavelength. Do we understand this?
Yes, sir.
But lambda is inversely proportional to z minus b square. Therefore, if z is more, lambda would be less. If z is less, lambda will be more. Therefore, if the first one is for atomic number z and the second one is for atomic number z dash has to be less than z. Do we understand this?
Yes.
Because lambda is inversely proportional to z minus b whole square. Yes or no?
Yes.
Have you noted this down?
Yes, sir.
Then I can give you this question to wind off today's class. There are K alpha series of two material or two metals are given with atomic number Z1 and Z2. Their accelerating voltage is same. Which atomic number is more? Which atomic number is less?
Z2 is more, sir.
Z2 is more. Z1 is Z2 is more.
Z1 is more, sorry.
Z1 is greater than Z2 because lambda 1 is smaller than lambda 2. Do we understand this?
Yes.
Well, then congratulations. We have come to the end of this historic chapter. X-rays and photoelectric effect and atomic structure is done. The next class we'll start with nuclear physics. That will consist of your same chapter that you have already done in chemistry. We'll do that. Did you get the sheet that I have sent you?
No, sir.
Lost in transition, I guess. So I will inquire as to where the sheets are, and I hope you will get it tomorrow, maybe today. I'll get in touch. Is there any doubt of what we have done in today's class?
No, sir.
Okay, then I'll see you in tomorrow's class, and we will start with nuclear physics. Take care. God bless you all. Bye bye.
Thank you, sir.